Okay, so this time we're looking again at the same function 1 over x squared, but now we're doing the integral from -1 to +1. And what I want you guys to do before I go through it is just pause the video, take about 2 minutes, do this integral using FTC2 and see what you get. Okay, so I'm going to assume that you have gone through. And so using FTC2, we know the antiderivative here should be fairly straightforward. We have -1 over x as our antiderivative, and we evaluate it from -1 to 1. And all we have to do now is plug in the limits of integration. Be a little bit careful because there are going to be a ton of negative values. We start off with -1 over 1 minus what we get when we plug in -1, which is -1 over 1. And so if we're a little bit careful here, we get -1, and then there's a triple negative actually on the second one, so we get -1, and our final answer here would be -2. And that should be the value of the definite integral here from -1 to 1 of x squared. However, if you think about this, what does this curve look like? 1 over x squared from -1 to 1. We notice right away this function is entirely above the x-axis from -1 to 1. And so there can be no way that this area is considered to be -2. Okay, the function is never below the x-axis, so definitely there's a problem, and this is a nice example to clearly see what happens when FTC2 fails. Okay, you'll notice that if you had done this integral a couple weeks ago, you would have not thought twice about it. Okay, you would have had your value of -2 and you would have moved on. But now you can see, taking this stuff into consideration, that this is a big problem. FTC2 fails us in this situation. And why? Why did FTC2 not work? Well, last time we were looking through, and we said that it's important to consider the conditions under which we can use FTC2. We said, yes, we do need to have a closed interval. Okay, and that is sort of the foundation for what we had with type 1 improper integrals. What if we had these infinite intervals on which we were trying to integrate? Okay, now we're looking at this second condition over here that we need our function to be continuous on. Okay, or it needs to be continuous on the closed interval. And when we look at 1 over x squared, it's pretty clear that we have this discontinuity occurring at x equal to 0. We have that vertical asymptote. Okay, and so the second type of improper integral is going to be exactly that. Okay, we're going to be dealing with discontinuities. So this, you have to know, this is absolutely not correct. Okay, we cannot do FTC2 in that way. So now let's take a look at how we should have done this one. Okay, and how we'll do these in the future. So here we have dealing with discontinuities, type 2 improper integral, and the approach is going to be fairly similar to what we had with type 1. We know that we cannot use FTC2 as is in this case because we have a discontinuity at 0. But what if we sort of stay away from that discontinuity? Okay, what if we find a closed interval on which our function is going to be continuous? So what we're going to do is right here to the left of 0 and right here to the right of 0, we can introduce some parameters. In other words, we can just do our definite integral on this region, okay, and then do a definite integral on this region. And on each one, we'll have continuity, and so we'll be able to do FTC2. So here, let's just fix this up a little bit. Let's suppose that to the left here, we are going to do the integral up until t. So that's going to look something like this. And on the right, let's suppose that we can use here s. And our integral would look something like this. So instead of doing the complete integral all the way from -1 to 1, what we're going to do is look at two integrals. Okay, so one integral will be from -1 up until t of 1 over x squared dx, and then I will be adding that to the integral from s up until 1. However, you'll notice that the way I've written this, these two integrals together are not the same as this. Okay, so what we have to do here with t on the side is that we're going to take a limit. Okay, as long as t is not equal to 0, okay, and more specifically, as long as t is to the left of 0, we are going to be able to do FDC2. So we can now take the limit as t approaches 0 of that first integral, and on the second integral we can also take the limit as s approaches 0. Okay, so again, we don't want s to be 0, but we can do the limit as s approaches 0. Now, fine, this looks pretty much set up, but we do need to be careful with one thing. Specifically, when we do the limit as t approaches 0 and as s approaches 0, so these two right here, these are not going to be just general limits, they're actually going to be one-sided limits. Okay, when we take t approaching 0, it needs to be approaching 0 from the left. Okay, and you can see that when we look at our illustration over here, t must be approaching 0 from the left. If t is to the right of 0, then we would have a discontinuity. So here, t is going to be approaching 0 from the left. Okay, and then for s must be approaching 0 from the right. Okay, and so whenever we're dealing with these discontinuities and we introduce the parameters, you will be dealing with one-sided limits, so make sure you set them up correctly. And now we can actually see what the value of this integral is supposed to be. So let's take a look. We will end up having to do two different limits. One as t approaches 0 from the left, we do our antiderivative, we get -1 over x evaluated from -1 to t, plus our second limit, and here we have -1 over x from s to +1. So we use FDC2, and then we can do our limits. So we have -1 over t minus -1 over -1. And we go to the second one, and we have -1 over 1 minus -1 over s. Okay, now we do have to be a little bit careful when we go to do these limits. So on the first one, t is approaching 0 specifically from the left. So this term is going to be approaching -1 over 0, but our t is approaching 0 from the left. And so this whole thing altogether, we have a constant divided by 0, so it will be infinite. But we can specifically tell that it's going to be going to positive infinity. Okay, because here we have a negative and here we have our negative. So fine, that first term is going to be going to positive infinity. So let's actually write out this first limit. We get positive infinity. Here, this is going to be on the second term, a triple negative, and it doesn't really matter. It's going to be -1. And then we have our second limit. Here we have, again, -1. But when we look at this term, okay, we'll notice that as s goes to 0 from the right, it's going to go also to some infinite value. We're going to get -1 over 0 plus. It's going to go to negative infinity. But here it's going to be sort of a double negative. So what we end up with on the second limit, we get plus infinity. And so really what we had was two limits, and both of them did not exist. Okay, so really thinking of this as an improper integral, we have our limits did not exist. What we're going to get is that the whole thing is positive infinity. It does not exist. The entire integral is divergent. Okay, and again, for improper integrals, that's really what we're interested in. Does the integral diverge or does the integral converge? So coming back up here, this region from -1 to +1 for 1 over x squared, that is an infinite region. Okay, that is a divergent integral.